Throughout learning about integral calculus, we've given you a ton of tools to evaluate definite integrals, and we've also given you a ton of tools to approximate or estimate definite integrals. And in this video, I want to add another tool to your toolbox in regards to estimating or approximating definite integrals. And mainly what we're going to be doing in this video is proving an inequality by using an easier to evaluate definite integral. So given this inequality here, why don't you try to find an easier to evaluate definite integral that can establish this inequality and prove it to be true? So why don't you pause the video and work on that? All right, assuming that you've given it a go, let's just kind of break down what we need to do here. Again, we're looking for easier to evaluate definite integrals, because when you look at this definite integral here, we don't know how to integrate 1 over the square root of 1 minus x cubed over this interval here. We don't have the tools to do that. But maybe we could find an easier to evaluate a definite integral that we know how to work with, know how to integrate, know how to evaluate, that would allow us to prove this inequality. So we just need to start to think of functions that we could integrate over this interval here that we know how to work with and that would hopefully be greater than this definite integral when we evaluate them. So let's see here. Just looking at this denominator, what if we were to try something like, I see an x cubed, what if we were to try an x squared, and we were to just have 1 over the square root of x squared? That would be easier to evaluate, so maybe we can try something like this. Let's try this guy. Let's try the definite integral from 0 to 1/2 of 1 over the square root of x squared dx. Because this would definitely be easier to evaluate. We just have 1 over x left over here, and we know how to integrate that guy. That's the natural log function. And then we'd be evaluating it from 0 to 1/2. But what's the problem with this? Well, when we evaluate the natural log at x is equal to 0, we have a problem. It's undefined. So this guy was a good try, but it's not going to work. So let's just continue to think about, okay, what other functions could we integrate over this interval that we know how to work with? And rather than getting rid of the 1 minus something like we did in this first example here, what if we were to keep it? What if we were now to say this? What if we were to say, okay, let's try now the integral from 0 to 1/2 of 1 over the square root of 1 minus, and instead of x cubed, let's try x squared dx. And do we know how to evaluate this guy? Well, yeah. This is the inverse sine function. This is the inverse sine function. And then we're going to evaluate that guy from 0 to 1/2. It's defined over this interval here, so we're good to go in regards to that. We know what the how to take the integral of this, how to anti-differentiate this, and we could get a value out of this. But now the major question is, okay, we found this easier to evaluate definite integral, but the question is, does this help us prove our inequality? And what do we want to ultimately happen? We want to ultimately say that this integral that we just found here needs to be greater than this other integral. That's our first step. That's our first step, is proving that the integral from 0 to 1/2 of 1 over the square root of 1 minus x cubed dx. And we need to prove that this guy is less than this other integral that we just found, is less than the integral from 0 to 1/2 of 1 over the square root of 1 minus x squared dx. If we can prove that to be true, we can go to the next part of this problem, but we need to first establish this. And in order to do that, you can notice, okay, we're integrating over the same limits of integration here, the same interval. So if we can prove that one function is greater than the other, well, then we can say that the area under the curve of that function is going to be either greater than or less than the other area under the curve, and thus we can prove that one definite integral is definitely greater than or less than the other. So what we're going to do is evaluate and figure out which function's greater than the other on this interval that we're interested in. So let's come down here and we're going to evaluate. We're going to figure out which integrand, which function is greater than the other. So we have 1 over the square root of 1 minus x cubed, and we're going to be comparing that with 1 over the square root of 1 minus x squared. And what interval are we interested in proving an inequality on? Well, we go from 0 to 1/2, so we're interested in that, 0 to 1/2. And the question is, do we include the 0, or do we include the 1/2? Do we include these endpoints here? Well, when we evaluate both of these functions at 0, we find what? We find that they're both 1. And we want to ultimately get to a strict inequality. So we're not going to be including 0 here. And when you plug in 1/2, we get different values. So we can include 1/2. Now, over this interval, we need to figure out which function is greater than the other. So what we can do is continue to whittle these guys down. So we can now, I want that in yellow. We can now look at, okay, how does the square root of 1 minus x squared compare with the square root of 1 minus x cubed? And then we can go even one step further. We could say, okay, how does x squared compare with x cubed over this interval? And in this interval here, again, we're less than 1, so x cubed is actually going to be less than x squared. And then when we take 1 minus that something and square root it, well, this inequality is going to flip. And then when we take 1 over that something, it's going to flip again. So we get this statement. And this is exactly what we were after. This is exactly what we were after. Because now we can say that this integral here that we were looking at as a candidate is definitely greater than this other integral that we're trying to prove an inequality with. And again, maybe this doesn't feel so good to you. Like, how can we say that there's a strict inequality over this interval here if we're not including 0? Well, again, these two definite integrals can be interpreted as areas under curves. So if I were to give you this, and these aren't going to be the exact functions here drawn out, but if I were to just play this out and say, okay, we're going to have a curve that looks like this maybe, and then we have another curve that starts at the same point, but is greater than the other curve over this interval that we're interested in. Well, you can see that the area under this curve, although they started at both the same points, that the area under this curve is certainly less than the area under this other curve. And that is what we just proved over here when we were looking at their functions. So hopefully you can feel good about this strict inequality. Now that we've proven that our candidate definite integral is definitely greater than this other integral that we're trying to compare with, now we need to see, okay, does this integral help us in proving this inequality? Specifically, that this definite integral is less than 2/3. So what we're hoping for when we evaluate this definite integral is for a value. And what kind of a value are we hoping for? Let's just say we were to evaluate this definite integral and got something like 0.7 or any value greater than 2/3. Would that be enough to prove this inequality here? Well, no, it wouldn't be. Because if we get a value greater than 2/3 out of here, well, then technically this definite integral could take on values from 2/3 up until that value, and that would not prove this inequality. But conversely, if we were to evaluate this definite integral and get a value less than 2/3, so let's just say we got something like 1/2 out of this, well then, yes, that would prove this inequality, because then we're saying that this definite integral will definitely be less than 1/2, and 1/2 is certainly less than 2/3. So that would be good. So we're really hoping that when we evaluate this definite integral that we get a value less than 2/3. So let's see if that's the case. Evaluating this definite integral, we get the inverse sine of 1/2, and then we have minus the inverse sine of 0. And we know that this is 0. So we really just need to look at, okay, what is the inverse sine of 1/2? And again, that's really saying this. The sine of some theta is equal to 1/2, and I always like to, sometimes I forget these things. I like to draw out some right triangles, and we have some theta value. We're having 1/2 over here, 1 square root of 3 over 2, and we know that theta is pi over 6. Theta is pi over 6. So this whole definite integral comes down to pi over 6. This is the moment of truth. Now we need to figure out, is pi over 6 less than or greater than 2/3? Well, pi is roughly 3.14. Okay, so that would be over 6 then. And we know that this is greater than 1/2, greater than 3 over 6. And then we can also say that a 3.14 over 6 is going to be less than, is definitely going to be less than 4 over 6. And 4 over 6 is 2/3. So we have just proven that this definite integral right here, that is easier to evaluate, is going to be less than 2/3. And earlier we proved that this definite integral is going to be greater than this other integral here that we are trying to prove an inequality with. And we've just finished the problem.